Fatima ma'am, did he answer the first question that you posted in chat? Okay, I will remind him. Thank you. Anish sir? Anish sir?
Yes, ma'am.
Sir is trying to connect in another system, it seems, for showing the demonstration of Qiskit.
Okay, ma'am.
And just check and where you need to allow.
He has joined, ma'am.
Wait, I'll ask in which name he's trying to join.
Yeah, okay, ma'am. I'll Srinivasan K only. I'll make him as. Yeah,
Unmute
okay.
him, unmute him. Yeah.
Yeah, okay.
Srinivasan sir?
Hi, am I audible now?
Yeah, yes, sir.
Yeah. So so far we have seen how to represent quantum state, and we have seen different representations like k-vector representation and the density operator formalism. And then we have witnessed what are the advantages when we are using quantum systems as well as quantum gates. It is better to visualize that right with some codes or something. Now we are going to use something called Qiskit. This is open source software. There we can simulate quantum systems and we can use it to realize some algorithms. We can even work with some algorithms with this. So the current today's plan is just to introduce how to use the Qiskit and how to get different representations of states using these kits and so on. I'll
So
start.
before going to that demonstration, can you please answer the two questions that is posted in the chat?
What is the first question, ma'am?
So first question is like how C transmitted in the sender side is received as C in the receiver side with the property of entanglement.
Entanglement. So we are not sending anything here, right? So we have a pair of systems we have when we have a single qubit system, the system can be in the quantum superposition. Now what is the situation? You have a source, that source emits pair of photon, and that pair the pair is entangled. That entangled in the sense you do the measurement on one system, that measurement outcome on the first system is going to disturb the measurement outcome on the second system. Because of that, there exist a non-local correlations between the measurement outcomes of the globe, both subsystem A and subsystem B. That is what we are realizing. We are not sending any properties here, right? Does it answer your question? Is it?
Fatima ma'am? The question has been posted by Dr. G. Fatima. Even she has asked the second question, sir.
Yeah. What is the second question?
Can you give a little bit insights on HTS gates? These gates are entirely new to us.
That's what we are going to do now, right? In the
Oh.
Qiskit, I will give you the demonstrations. Suppose if you initialize the system in some quantum state, and if you do this operation, Hadamard operation, and this yes operation or C naught operations, what's going to happen for the system? That I'm going to demonstrate it now, right? I'll share you the screen now. Are you able to view my screen?
No.
Oh yeah. Now, are you able to see view my screen?
Yes, yes, sir. Yes, it's possible.
So now I'm going to like give you a little bit insight on how to install the Qiskit and like how to work with this. First thing is like here with this Qiskit simulation software, like we are going to visualize the quantum, we are going to visual representation of quantum states, and then we can even print the state of the system, or else if you construct some unitary operator like quantum circuits, for the whole circuit we can construct some unitary operator. Everything we are going to visualize using the Qiskit simulation software. So first thing is like there are two things here. One is you have to open an account in this IBM Quantum Learning. For that, like you go to this IBM Quantum Learning website, and there you can go for this sign in. And then like if you already created some account, okay, otherwise you can create an account. For example, I'm linking my Google account with this IBM, and I already did this. So here, once you do this, like you will get a token, IBM token, and you can copy that from this IBM's website. Okay, so you can copy the token, and then later on, yeah. First, for installing Qiskit in your laptop or a computer, you have to use this following code. That is pip install Qiskit. And for every command, you have to use just not a enter. If you enter, it goes to the next line, and you have to use command shift enter. And in that case, like it is going to install the Qiskit in your thing. And then you have to use something called this pip install kaleidoscope. And like for that also, after typing that one, you have to press shift return, that is shift enter. Then it is going to install this Qiskit in your PC. Once it is installed, then we can use this, like from Qiskit we can import whatever packages we want to work. For example, here I'm from Qiskit import IBM Q, and from the license like IBM token, like once you create a ID in your IBM learning website, you will get one token, and you that's the number, like a very huge number you will be getting, and you copy the code token and paste it here in the command ibm.save account. There you have to copy this IBM token, and then IBM Q.load account. If you press, then your account will be installed in your PC. So for that, like we are working in this Jupyter notebook. So first you have to install Anaconda recent version, and in the Anaconda, for example, if you install this Anaconda, there from you can launch this Jupyter notebook. If you launch this Jupyter notebook, you will get this site. There you have to do all these things like this installation of this Qiskit kaleidoscope. After that, you have to load your account in this Jupyter notebook. Once everything is done, then you can work with Qiskit, right? And most of the times, like we'll be using this pi, square root, and other symbols. For that, you have to import NumPy Python package, and we can use short notation for that NumPy as something like NP. And for using this Qiskit visualizations, we have to import following things. That is import array to LaTeX command. That means like you are having a quantum state and you can print its state as a LaTeX command. So for that, you have to use array to LaTeX, or else you can visualize the system as the histogram. Don't bother. I'm going to spend time on each things. So just I'm introducing the installation part to you. And we can use something called a block vector, that is a visual representation of a quantum state, and so on. So first thing, what is quantum circuit? So same like a classical circuit. What we can do, like so for example, you look at this circuit. In classical circuit, when you have a wire, that means you have a electronic circuit. In that there is a wire that takes the information from one point to the other point. For example, in the quantum circuit, it is not like in the left side, you will be having a quantum state. Here this Q0, Q1, Q2, Q3, Q4, Q5 are quantum states. And when you are using QUBIT, all the time the system will initialize the system in the get 0 state. Okay, it is going to initialize everything into the get 0 state. After that, in classical circuits, what you will do, you have some input state, and you are going to use series of gate operations on that state, and you are going to have some output state. And the same thing holds here. You have an input state, and that is going to be a quantum state instead of classical bits. So these are quantum bits, and all the bits are initialized in the 0 state. After that, we are performing some gate operations on the initially prepared state, and the system is evolving. And later time, we are going to measure the system and find out what is the probabilities or what is the state of the system. That's what you are going to realize. So here, so first we will create one circuit. For example, I'm going to create a first circuit in the name, let's say RKM, that is equal to quantum circuit. For example, we can define how many number of qubits you want. For example, if you want just only one qubit, just give 1. That means you have a quantum circuit in the name RKM, and you are going to have only one qubit in your circuit. And if you define that one, and you can draw the circuit. For example, here, if you look at, I have created a quantum circuit with 3 qubits. So here you have a circuit with 3 qubits, and I have named that circuit as circuit. Okay. And then I want to perform these gate operations, for example, and still I haven't introduced what is this Hadamard gate and CNOT gates and all. Let's assume there exists some gate, but later on I will introduce what is this gate. I want to use these 3 gates. First gate is Hadamard gate. And if you look at carefully, that Hadamard gate is operating on only the first qubit, that is 0th qubit. And this CNOT gate, second gate, that is operating between first and second qubits. And the third gate, another CNOT gate, that is operating between first and third. So suppose if I want to use that one, so what I'm going to do, create a circuit with 3 qubits, quantum circuit 3, and then I'm going to store it in the name circuit. If I have to apply some operator here, the circuit is the name of the quantum circuit. Circuit dot h of 0. H means Hadamard operator. H of 0. 0 means it is going to operate on 0th qubit. And circuit dot cx of 0, 1. That means there exists a controlled NOT operation. What it does, the controlling qubit is going to be 0th qubit, and the target qubit is going to be first qubit. So this CNOT operator is operating between 0 and 1. That is, 0 is the control qubit, 1 is the target qubit. And we can define the position informations here. And third gate is CNOT gate, that is operating between first and third qubit. So circuit.cx of 0, 2. Next, what we are going to do, like after defining this circuit, we are going to measure the system, right? So circuit.measureAll. MeasureAll means it is going to measure what is the state of the system for every individual qubit. So if you define measureAll, that is going to measure every one of the qubit. And circuit.draw. Suppose if you want to draw the circuit, you have to use circuit.draw, and that is going to draw the circuit. Okay. So for example, here, first circuit we have created is quantum circuit with 1 qubit, and we stored it in the name RKM. Now, just I'm going to draw the circuit, nothing more than that. For that, what we are going to do, our circuit name is RKM dot draw. So RKM dot draw means it is going to draw that circuit. And after that, you have to press Shift Enter. If you press, so this is the simplest circuit we have measured without any gate. Okay, so we don't have any gate here. Just you have created a circuit in the name RKM with only one qubit, and that is Q. That system is initialized in the Q, and then we are just drawing that circuit. Okay, now what we can do, we can do some gate operations. But before that, generally when we are working with the quantum circuit, like we will be having both quantum and classical bits in the circuit. Why we need a classical information? Because if you look at this circuit carefully, we have created a quantum circuit with the 2 qubits, and we have done some gate operations. After that, we measure the system. When you measure the system, what happens? The system is going to collapse into one of the eigenstate, and that is going to give you some values, right? The classical information. That is, once you measure the quantum system, that is going to give you some number. That numbers will be stored in the classical register. So there exist 2 registers. One is quantum register, that is going to tell you how many qubits you have and what are the gate operations you are going to do on that quantum register. So this is the actual quantum circuit. And there exists a classical register. That classical register, what it does, like it is measuring the qubit 1 and storing that information in the classical register 1, and it measuring the qubit 2 and storing that classical register information in the register 2. So now we can, when you want to have this classical register, just press how many, just give you the number that is going to tell you how many classical registers we want and how many quantum registers. So now I'm just modifying the circuit. I have a quantum circuit with 1 qubit, 1 quantum register, and 1 classical bit in the classical register, and then I'm drawing that circuit now. So now what happens? I have a simplest circuit with 1 qubit and 1 classical bit. That is, you have a quantum register that is initialized with 1 qubit and 1 classical bit. So whatever you do some gate operations, and after that, if you measure the system, you are going to get its outcome here. So now what we can do next? Now let's measure the system and see what is the state of the system, right? So when you measure the system, like what are the ways in which we can visualize the system? Like once you can plot histograms like this, right? That is going to tell you what is the state. It is 0 state or 1 state, and how many times it is collapsed into the 0 state, or and how many times it is collapsed into the state 1, and so on. So for that, we have to use this simulation packages, that is AER simulator, that is defined in this Qiskit. And after that, from the Qiskit visualization softwares, we have to import following things. One, if you want to have a histogram, you have to import plot histogram, right? So it is already imported. Now what I'm going to do, I'm going to use this command for our circuit. Our circuit is in the name RKM. So now what happens here? You have a quantum bit that is initialized in the ket 0 state, and you have only 1 qubit and 1 classical bit, and you are measuring the system, and that information is stored in that classical register. So now what I'm going to do, I want to plot the histogram for this whole thing. So I want to have a histogram. So since our state is a quantum state is ket 0, so you look at here, the state is 0. And what happens, like when we are running that in the QUBIT, the QUBIT is going to run the whole thing for 1024 times. Like when you initialize the system, it is going to measure the system in 1024 times. After that, it is going to tell you how many times this 0 state is measured. Since our state is very simple, right? It is get 0. So it is not in a quantum superposition. It is just get 0. It is like a classical bit. So now when I measure that system in this get 0, like all the 1024 times, we found the system in the 0 state. That's the meaning of this one. So all the 1024 times, we found the system in the 0 state. Now I'm going to do some small modification in the circuit. Like I'm going to do some gate operations. So someone asks me, what is this Hadamard gate? Now let's realize what this Hadamard gate does. So now in the same name RKM, I have created a quantum circuit with 1 qubit and 1 classical bit. After that, for the circuit RKM, I'm going to apply Hadamard operator for the 0th qubit. That it starts with 0, position 0, so 0th qubit. Now let's see what happens. So you have a quantum circuit, the system initialized in the get 0 state, and we are applying Hadamard operator. When this Hadamard operator acting on the 0 state, that creates a quantum superposition, and the system will be in the quantum. So as we mentioned earlier, it is like you have a horizontally polarized light, and you are rotating the polarization state to 45 degrees. So this Hadamard operator is like rotating the horizontally polarized light to 45-degree polarized light. So when you have a 45-degree polarized light, that is going to have equal superposition of H and depolarized light. So that is, it is a quantum superposition of 0 and 1 state. So I'm making this circuit like you have a quantum bit and you're measuring like applying Hadamard operator and measuring the system. The outcome is going to be stored in this classical register. Now what we have to do, we have to plot the histogram and realize what happens. Let's see, before this, like before applying this Hadamard operator, we found the 0 state in all 1024 times. Now let's see what happens to the system. See here, we are running the circuit for 1024 times. So 553 times the system is found in the 0 state, and 471 times the system is found in 1 state. That means this Hadamard operator creates a quantum superposition of 0 and 1 state. So the state of the system will be 1 by root 2 times get 0 plus get 1. So because of that, the system can randomly collapse into the 0 state or else 1 state with the probability 1 by 2. So what is the probability for 0 state? That is 1 by 2. And what is the probability for 1 state? That is 1 by 2. So here, the total number of events is going to be 1024. And number of times the system collapsed into 0 is 553. So 553 by 1024 is close to 1 by 2. And 471 by 1024 is close to 1 by 2. So it is like tossing a coin. When you say coin is a fair coin, it has an equal probability for horizontal and vertical. So sorry, head and tail. But when you toss the coin 1024 times, it is not guaranteed for you to get 512 head and 512 tail. You may be getting one above the other, right? So head probability for horizontal and vertical, though it is 1 by 2, the number will be slightly different. So in order to make this probability equal to 1 by 2, what do we have to do? We have to measure the system for very longer number of times. So in 1024, we will see. But if you next time when you measure the system, the number will be different. So now you see it is going to be 1520 and 504. And you measure, like, meaning is 520 times you found the system in the 0 state, and 504 times you found the system in the 1 state. You do the measurement again, the number will be different, right? So here 533 and 491, you measure it again, the number is going to be different, right? So that's what's going to happen. So this is the very simplest case. So what we are doing, we are initializing some quantum circuit with only 1 qubit, and we are storing that in the name RKM, and we are just applying a Hadamard operator. Next, we can look at NOT gate, right? For example, what is not gate? So it is going to flip the quantum states. If you send a 0 state, that is going to give you 1 state, or else if you send 1 gate, that is going to give you 0 state. As I mentioned earlier, whenever you initialize the system, it is always initialized in the 0 state. Now, instead of this Hadamard operator, what I'm going to do, I'm going to apply Pauli X operator on the system. So instead of this Hadamard, I'm going to use Pauli X operator. When I use Pauli X operator, this is the circuit, right? You have a 1 qubit and 1 classical bit, and you are applying Pauli X operator on the initially prepared state, and you are measuring it. Now we will use this visualization software, and what is going to happen? So what is your guess here? You have a system, that system is initialized in the 0 state, and afterwards you have applied Pauli X operator to that. So when you apply Pauli X operator, that is acts like a NOT gate. So the 0 state will be flipped to 1 state. Okay, so we'll see what happens here. So you see here, we measure the system certainly in the 1 state, like all the 1024 times, the system is found in the 1 state. So that's what this Pauli X operator does. Okay, so we want to have some idea about what is Z gate. So this Pauli X gate flips the quantum system. Like if you send a 0, that is going to become 1, and if you send 1, that is going to become 0. That's what it is, right? So what we can do, we apply another X gate. RKM is the circuit name. I'm going to apply another X operator. So what we can expect here, you have a circuit in the name RKM with only 1 qubit, and first I applied X operator to the 0th qubit. Because of that, the state is changed to 1. So get 0 is changed to 1. Now again I'm applying like X operator. When I apply X operator here, what is going to happen? The 1 state again going to change as 0. So first draw the circuit, right? So this is a circuit. First I initialize it in get 0. After this X operator, it becomes get 1. After again this X operator, it becomes again get 0. That we can visualize using this histogram, right? So see here, now the system all the time, it is found 1024 times, it is found in the 0 state. So it is certainly is in the 0 state. So this X operator is the self-inverse operator, right? You do that operation twice, that is going to act like an inverse. So next we will mix this X operator and the Hadamard operator, right? Earlier we measured this Hadamard operator and we found the system in the both 0 and 1. And if you apply both, that is also possible. Like you first you do X operator to the system, and next you do Hadamard operator to the system. So X and H both are going to act. Now if you measure the system, that is going to be in the quantum superposition of 0 and 1 again. Okay, now we will strengthen ourselves, like we will go to the multi-qubit case. Before we are entering into large number of qubits, let's restrict ourselves to 2 qubit system, right? So next circuit is, I'm going to use something called Bell state. Like already we have seen that Bell state, like HH plus VV by root 2. If you are writing it in this bits notation, it is going to be 0, 0 plus 1, 1 by root 2. Let's see how to generate such circuits. So it is going to be quantum circuit with 2 qubits. So now we are going to generate a quantum circuit with 2 qubits. And what are the catches there? So it is going to be for creating this Bell state, we have to use something called Bell dot H of 0. That is, I'm going to apply Hadamard operator to the first qubit, and then Bell dot Cx on 0, 1. That means it is going to apply Cx means controlled NOT operation. What is controlled NOT operation? Here we have witnessed what is NOT operation, that is X gate. When it is applied on the 0 state, the state will become 1. When it is applied on 1 state, the state is going to become 0. So 0 is turned to 1, 1 is turned to 0. That is NOT operation. But this controlled NOT operation is very peculiar. That is, I'll explain to you with the circuit. So here, bell dot draw so this is the circuit. So this is the circuit to create a bell state, like maximally entangled state. So here we have a 2 qubit and the circuit is named as bell, and bell dot h of 0 means it is going to apply Hadamard operator on the first qubit. So first qubit initially it was in 0 state, both the qubits. Now when I apply a Hadamard operator to the first qubit, I'm not doing anything to the second qubit. So that means identity operator is acting on the second qubit. And when I apply Hadamard operator to the first qubit will be left in the quantum superposed state. That is, it is 1 by root 2, 0 plus 1, but 0 plus 1. Afterwards, we are applying something called C0 operator. What is C0 operator? Here there exists 2 qubits, right? One qubit is called control qubit, other one is called target qubit. This controlled NOT operation, like whenever first qubit is in the one state, the state of the second qubit will be changed, right? Whenever first qubit is in the one state, state of the second qubit will be flipped. For example, let's say if I am applying 0, 0 to the first qubit. If I am applying 0, 0 here, so this is the circuit. Just we will understand what is the C0 operator. So you have a 2 qubits, both the qubits are initialized in the 0, 0 state. And when you apply the C0 operator, we'll see what is going to happen by measuring that system. So what we have to do, we have to use this histogram. Instead of RKM, we are using the circuit name bell. So look at this. So we have 2 qubits and both the qubits are initialized in the 0 state, and just we are applying Hadamard operator, nothing happened. That 0, 0 is there as it is, right? Nothing happens to this. But when I have my first qubit in the one state, that means I'm applying bell dot x of 0. That means you have 2 qubits, both of them are initialized in the 0 state. Now I am applying a x operator to the first qubit. After this x operator, the first qubit is going to become one state. Okay, so let's see without this C0, what is the state? Without the C0, right? This is the state, and if you measure it, what you are going to observe? You are going to observe 1, 0. So you have to get it in the reverse order. It is 1, 0, right? So that is the state. Means you initialize both the qubit in the 0, 0 state, and after that, when you apply x operator to the first qubit, that state becomes 1, 0. Now I'm going to apply C0 operator to this one. So the bell dot Cx, controlled x, and the 0th qubit is control qubit, first qubit is the target qubit. Now this is the circuit, like the state becomes 1, 0. When I apply control NOT operator, whenever control qubit is in the one state, the target state will be flipped. So this is the case, like 1, 0 is the initial case. Now after the C0 operator, what is going to happen? Since the control qubit was in the one state, the target qubit state is flipped. Okay, so this is the C0 operator. C0 operator is a controlled unitary. Earlier, NOT operation is just a unitary operator. Wherever you apply, it is going to perform NOT operation. But this control NOT operation, whenever the control qubit is in the one state, the NOT operation will be applied on the target qubit. So that's the catch here. And for example, if you apply x operator to both, bell dot x of 1, that means you are applying x operator to both the gates. That means initially you prepared 0, 0 state. After this X gate, the state of the system will become 1, 1. Now we are sending this 1, 1 to this control NOT operator. You are sending 1, 1 to this control NOT operator. Since the control gate is in the 1 state, the target will be flipped. So if you are sending 1, 1 to this control qubit C0 gate, this becomes 1, 0. So that you can visualize here. So right, that becomes 1, 0. That's it. Right. So this is how the C0 gate works. Now we will prepare the maximally entangled belt state. So for that, what we need a Hadamard operator to the first qubit, and then you are going to apply the C0 operator. So this is the circuit to create the belt state, and when you run this circuit, you look at what happens. The system is found in the 0, 0 state half of the time, and 1, 1 state half of the time. So that means whenever you find the first system in the 0 state, wherever the second system is located, it may be located anywhere in the universe. Like if you measure the first system in the 0 state, the second system always going to be in the 0 state. It is going to collapse into the 0 state. And same way, whenever you find the first system is collapsed into the 1 state, the second system, irrespective of the distance, wherever it is located, that is also going to be measured in the 1 state. So there exists a non-local correlations between the measurement outcome. So the system is found out in the 0, 0 state 516 times, 1, 1 in the 508 times. So it is some simulation packages. Like if you run it again, like it is going to give you different result, right? So 502 times it collapsed into the 0, 0, and 522 times it collapsed into the 1 state. So that's how it works. And you can even create other belt state. Like for example, can I have a cross correlations? Like first, whenever I found the first system in the 0 state, can I make the second system in the 1 state? Yeah, it is also possible. For that, what we have to do, we have to use one Hadamard like X operator to the second qubit. So like bell.x on 1. So what we are doing here, initializing 2 qubits in the 0, 0 state, and I am applying Hadamard operator to the first qubit, Pauli X operator to the second qubit. Because of this Hadamard operator, the first qubit is in the quantum superposition of 0 and 1. And because of this X operator, second qubit will be in the flipped state. That is 0 turns out to become 1. After that, we are applying this C0 operation. And you can guess the state here. The state will be 0, 1 plus 1, 0 by root 2. So look at this state. The system is measured in the 0, 1 state 515 times and 1, 0 state at like number of times it collapsed into 1, 0 state is 509 times. That means whenever you find the first system in the 0 state, second is going to be in the 1 state. And here, whenever the first system is in the 1 state, second is going to be collapsed into 0 state. So there exists a non-local correlation, that is entanglement present in the system. Now, what are the other ways of visualizing the systems? Like we can use something called Bloch-Spear representation, or else we can even print the quantum state as the array to LaTeX command. We'll go one by one. For example, now I'm going to use another circuit with 6 qubits, right? So what we are doing here, we are creating a quantum circuit with 6 qubits, and I'm going to save that circuit in the name QS. And if I want to apply some gate operations on that one, what I have to do, QS dot X of 1. That means I'm not doing anything to the 0th qubit, but for the first qubit, I'm applying X operator. Second qubit, I'm applying Hadamard operator. Third qubit, I'm applying X operator. Fourth, I'm applying Hadamard operator, and so on. And if I print the circuit, this is how it is going to look at this. It is just a simple circuit. And okay, since I have run this circuit already, it is, so this is how it is. Like what I'm doing, for 0th qubit, I'm not doing anything. For first qubit, I'm just applying X operator. Second qubit, I'm just applying Hadamard operator. Third qubit, I'm applying both X and H. Fourth qubit, I'm just applying Y operator. Fifth qubit, I'm applying X and Z, X and Y. So now what we can do? We can measure the system and find out what are the states. So if you want to print the state, we can use this command. For example, for our old circuit, this simplest case, we can even print what is the state of the system, right? Okay. RKM is our first circuit. Just we'll see what is happening with that RKM. So look at this. The state of the system state vector is 1 0. 1 0 means it's in the 0 state. Okay. For example, here for the same RKM circuit, that is with only one qubit, I'm just applying X operator and the Hadamard operator. So the circuit is going to look like this. So what is your guess here? When you apply X operator to 0 state, that becomes 1. After that, if you apply Hadamard operator, the state will become anti-diagonal. That is 1 by root 2 and minus 1 by root 2 that we can use. So this is the command to get it as the LaTeX visualization. So you look at, so this is a state. Root 2 by 2 is again 1 by root 2. So 1 by root 2 minus 1 by root 2 is the quantum state after this operation. And if you are just applying Hadamard operator, this is going to become 1 by root 2 and 1 by root 2. There will be no phase factor here, right? And if you are doing the same for this 6 qubit state, so this is the state we initialized, and we have applying series of gate operations to initially prepare the state. Now I want to have the array to LaTeX command. I'm going to use this one, and that is going to print it as a LaTeX command. Let's see what happens with that for that 6 qubit system. So let's first again print this 6 qubit case. So this is the state. So we want to have visual printing representation for this one. So I'm going to use the same command. And then instead of RKM, our circuit name is QS here. QS. If you do this, so this is the state, like what you're expecting. You have a 6 qubit system. So the dimension of the Hilbert space is going to be 2 power 6. That is going to be 64 cross 1 dimension. So that's what we are getting. And for example, even if you erase some like gates, change. So this is the circuit, new circuit. And for the new circuit, what is the state? So this is the quantum state, right? And even if you apply one more Hadamard operator here, QS dot H of 0. And this is the new circuit, and we are applying Hadamard operator to 0th qubit. And then we want to have state of the system. So this is going to give you the state of the system as this array to LaTeX command. And you can even print the unitary operator, whole unitary operator associated with that one. So what are the things we have visualized so far? So first thing is we have understood how to create a quantum circuit. So for that, what we are going to use? The command quantum circuit, and you can define how many number of qubits you want, and you can save it in some name. And after that, if you want to apply some gate operation, use that name dot operator and which position you want for first qubit or second qubit, whatever qubit, and you can measure it and draw the circuit using this command. After drawing the circuit, you have to visualize, like, right, what happens to the system. It can be either a histogram plot or else this array to LaTeX command that is going to print the direct state as it is, right? So now for this circuit, we'll see what is the visualization. For example, we created the build state, right? So this is the build state, and let's see what is the build state we are getting using this array to LaTeX command. So this is the build state, and when you use this array to LaTeX command, that is going to print the quantum state straight away instead of visualizing that one. So here we have to use the name build. So because that's the circuit name, build. Then so this is the state, right? So this is what you're going to get as the output. And if you change the circuit, this is how it's going to look like. Okay. Now, so what else we can think of? We can think of something called block sphere representation. So for example, you look at this one, right? I'm going to create a quantum circuit with 6 qubits. So how many number of qubits I'm using? 6 qubits. And the circuit's name is Q1B. And what I'm doing here is I'm just applying Pauli X operator to second qubit and Pauli X operator to third qubit. And I'm using this command like for I in range 6. That means the I is going to run from 0 to 5. And for this like this Q1B, that is this circuit, it is going to apply Hadamard operator. And then I'm using something called phase operator, like what phase I want to introduce between H and V component and which position I'm going to use that gate operation. Everything is defined here. And afterwards, what we can do, Q1B dot so this is the circuit, and we can visualize like this block sphere representation. So for the block sphere representation, we have to use this command. So look at this one, right? So the first qubit is in the diagonal polarization. Second qubit is in the diagonal polarization. Third and fourth are going to be in the somewhere between 0 and 1. And fourth qubit are going to be in the right circular polarization. So we can have a visual representation using this block sphere representation, right? Now let's visualize what happens to this simple cases, right? Now I'm going to create a circuit, and if you want to have more insights on this, how to use this one, you can go to something called like here QUBITS textbook. If you go in Google, you will go like that will direct you to some GitHub page, and you go to this GitHub page, and there you can see like this QUBITS textbook, and that has all the notes in it, right? So you can get the notebooks, and if you want to have the idea of algorithms, like a lot of algorithms are defined in this one. So what we are going to do, right? Just type QUBITS textbook in Google. That is directing you to this GitHub page. In the GitHub page, like you can get everything. So this is the GitHub page, and there you go to this notebooks or else this QUBITS textbook. That will take you to every chapter one by one. Like you can have like introduction to representing qubits. So how you are representing a qubit and what happens when you apply Hadamard operator. So here there is another example given. So here, if you look at carefully, So what is doing, like they are creating a quantum circuit with only one qubit, and it is stored in the name QC. Right? Straight away when you use it, what is going to happen? The system will be initialized in the 0 state. But instead of that, if you want to initialize the system in some specific state, that you can define. Like here, it is defined initial state is 0, 1. And what we have to do for that? QC dot initialize initial state, 0. That means for 0th state, you are going to initialize this state and you are drawing that circuit. Okay. So suppose if you want to initialize the system in some other state, right? We can define that one. 0, 1. That means like vertically polarized light. So this is what it is going to happen. And if you don't use this MPL, it is going to be like this. Yeah. So now the system is initialized in the 0 state instead of 1 state instead of 0 state. That state initialization we can use, right? And this is what single qubit gate operations, like from the Qiskit textbook, you can get this X operator, Pauli X operator, you know, right? 0, 1 and 1, 0. And when you apply this X operator on 0 state, the state will become 1. That get 0 is turning to 1. And when you apply Hadamard operator, this Hadamard operator is given by this matrix 1 by root 2, 1, 1, 1 minus 1. 1 by root 2, 1, 1, 1, 1, 1 minus 1. So this is what you are going to get. And if you are using this array to LaTeX command, I already told you, you can use it to represent both the quantum state as well as gate. For example, here we are dealing with 2 quantum gates, and each gate is of dimension 2 cross 2. And when you take a tensor product of these 2 gates, it is going to result in something called 4 cross 4 matrix, right? It is simplest case. Here you can do what we can do, like just multiply these 2 gates and you can find out what is the unitary operator associated with this whole circuit. But when you are dealing with some 10 qubit system or 15 qubit system, the Hilbert space dimension is going to grow exponentially. For example, even for 10 qubit, so the Hilbert space dimension is 1024. So that means the unitary operators involved in that circuit is going to be of dimension 1024 cross 1024. So in that case, it is not easy for you to multiply the gates and get what is the final gate you are going to get. In that case, what we can do, you can use this command, right? Get unitary, and then print it, use this array to Qiskit visualization software and the array to LaTeX command, and you can print what is the gate operators involved for the whole circuit, right? Even if you are dealing with very big circuit, just use this one, and that's going to give you what is the unitary gate associated with the whole thing. For example, for this, let's see, for this circuit QS, so this is the circuit, and we will use this array to LaTeX command. Then yeah, so for example, you have a 6 qubits quantum circuit, and that circuit is in the name QS, and we have applying series of unitary gate operations to that circuit. And after this series of gates, we are drawing just the circuit. Now, what is our idea? You have a 6 qubit system. So what is a Hilbert space dimension? Each qubit with the dimension 2. And when you take a tensor product of all the 6 qubit, the Hilbert space dimension is 2 power 6. That is 64 cross 64. The unitary operators are going to be 64 cross 64. And the quantum state is of dimension 64 cross 1, right? So what is the state? Like you have these many gates, like 7 unitary gates are there. if you take a tensor product of all the 7 gates, what is going to happen? Like if you are working with pen and paper, it may take some days, but just use this array to LaTeX command and AER simulator, and you can get the unitary operator associated with the whole circuit. So this is the 64 cross 64 dimensional unitary operator associated with the whole circuit. Okay, and for example, if you are working with that bill, for we have already witnessed what is happening to the bill state. For the bill state also, we can construct like what is this unitary operator. For example, earlier we worked for the bill state. There you can use this one, and then you have to change the name to bill. And use this array to LaTeX command to print the unitary operator. Since we are just dealing with a 2-qubit system, so it is going to be of dimension 4 cross 4. Now we want to get what is the unitary operator associated with that. So this is the 4 cross 4 matrix associated with this particular circuit. So next thing we can do is to see what is the visual representation for both the qubits after this gate operations. So for that, what we have to use? We have to use this block multivector representation, right? Here the circuit name is bell. So next thing, like here we have initialized either as a system defined state, or else we can define our own state for the initial state, and then we can run the circuit. And this block sphere representation is the alternate representation, like a visual representation. Other things are just going to be an equation, and this is going to be a visual representation. And we can work with different single qubit gate operations that we can define here. So we know this Pauli gate, that is when it is acting on X state, it becomes 1, and when it is acting on 0 state, it becomes 1, and 1 state it becomes 0. And then we can have this Y and Z gate, right? This is going to be introduced some phase difference between X and like a 0 state and the 1 state, that we can clearly see by applying. For example, you create a quantum circuit in the name, let's say QB equal to quantum circuit 1. The name is QB, and then applying QB dot Hadamard operator to the first qubit, right? And then QB dot draw. So this is a very simple circuit with only one qubit, and I'm just applying Hadamard operator. Now I want to see, like, I want to visualize what happens when I'm applying a Pauli Z operator or Y operator to the circuit. So we'll go step by step. First, we will use this array to LaTeX command and visualize what is going to happen to the state. To be. So the system is initialized in the 0 state. After that, I applied Hadamard operator. This Hadamard operator, I already told you, it is a quantum superposing state gate. So because of that, this 0 state is undergoing unitary evolution, and it changed to 1 by root 2, 0 plus 1. That means 1 by root 2, 1 by root 2. This is a 2 cross 1 matrix I'm getting. Now, what is my idea? I want to have like a representation, like what happens when I'm applying this Pauli Y gate, right? Just apply Y on the 0th qubit. After this Hadamard operator. So initially it is in 0 state. After this Hadamard operator, you are creating a quantum superposition that is 0 plus 1 by root 2. Now when you apply this Y gate, that is going to give some phase difference between, that is a phase difference between H and V polarization, that is 0 state and the 1 state, right? That we can see clearly here, right? So what happens? It becomes minus I by root 2 and I by root 2. So it is going to introduce some phase difference between the states. And if you, same way you can visualize what happens if you apply Z operator instead of Y. So when you apply Z, right, it becomes, earlier it was in the diagonal state, that is 1 by root 2, 1 by root 2, that becomes my anti-diagonal, that means minus 45-degree polarized light, that is 1 by root 2 minus 1 by root 2. So similarly, we can visualize different quantum gates. And then, yeah, this is what the Hadamard operator, Hadamard gate. So when this Hadamard gate is like the matrix representation for that is 1 by root 2, 1, 1, 1 minus 1. So this is what happens. When this Hadamard operator acting on 0, that produces diagonal. When the Hadamard operator acting on 1, that produces anti-diagonal state. That we have already seen in the Qiskit. And like when we initialize in some state and then you do the Hadamard operation, you can visualize using this gate. And this is a phase gate. What is this phase gate? The phase gate is defined in this way, like QC dot P of pi by 4, comma 0. So what is the meaning? It is going to have like 100 e power I phi as the matrix representation. This phi is going to be defined here. This pi by 4 is nothing but the phi value. And here the 0 is which qubit it is going to act on. That is what it is. For example, we'll have here, we'll modify the circuit with the 2 qubits. And for 0th qubit, we are applying this gate. And for second qubit, QB dot H of 1. And then I'm going to apply QB dot the phase gate P with pi phase I want to add, comma first gate, right? I can apply it on any gate. I'm going to give the position information as 1. So this is what to keep. P dot pi. Okay, so now we created a quantum circuit with the 2 qubits, and then what we are doing, we are applying Hadamard operator to first and the second qubits, and the Z operator to first qubit, P pi on the second qubit. But P pi is nothing but e power minus I pi, that is going to be minus 1 again. So that is again a Z gate. So what we can do, we can define some different phase, that is pi by 2. And now we will visualize the state. So this is going to be the quantum state now, right? And if you want to plot the histogram, that is also possible, right? And we have to use the same command. So what is the meaning here? So by looking at this equation, we can say the coefficients C1, C2, C3, C4s are 1 by 2 minus 1 by 2, 1 by 2 minus 1 by 2. From this, like we can say, what is the probability to measure the system in different eigenstates? That is going to be 0.25, 0.25. Everywhere it is equal, right? So this is what it is. So what we learned so far, we have learned how to like install Qiskit in your PC, and then how to get the IBM token and then get a package for you. Afterwards, what we have done, like we have used this Qiskit textbook, and with that, like we can work with any circuit or else any algorithms. And then we have discussed about how to create a quantum circuit and how to apply some gate operations on the circuit, and how to modify the initial state to the final state. And later on, we have seen how to measure the qubits and how to store its information on the classical register. So that we have discussed. So once we store the information in the classical register, what we can do, we can visualize the system in multiple ways. One possible way is to look at this histogram, and we have seen it is a probabilistic thing. You would run this one multiple times, that histogram pattern will be changing. Then afterwards, we have witnessed another visualization package that is called the block vector representation. Actually, I didn't introduce this block vector formally, but in the process, like in the workshop, someone might have introduced what is block vector representation. So if you know that already, like you can use this Qiskit command to get the block vector representation for your quantum state. And another possible way is to have array to LaTeX command. That is, you use the array to LaTeX command, and using that array to LaTeX command, you can print the quantum state as it is, how you are writing the state of the system in pen and paper. Same way, you can write the quantum state of the system using this array to LaTeX command, and you can use the same array to LaTeX command to get the unitary operator associated with it. For example, if you are working with some complex circuits, the matrix dimension is going to be more and more, and in that case, that number of elements involved in that unitary operator is going to be very large. Even in that case, just use this array to LaTeX command to get the final unitary operator associated with it. So these are the things we can learn. And then you can use something called general unitary operator. Like that unitary operator, like any gate you want, you can create from this one. For example, if you want to have a Harman operator, just change this kita phi lambda values. That is going to give you Harman operator. If you want a phase gate, that you can do Pauli operators or any rotation matrix. Anything you can generate with this U gate. Let's discuss like how to use this U gate. So here you see you have created a circuit with one qubit, QC.1, and then we will. So here there is a circuit with only one qubit, and its name is QC. For that QC, I'm just applying this unitary operator. What is the importance of this unitary operator? This unitary operator with this, like it is like a universal one. Whatever gate you want, you just change this theta phi lambda values to construct any gate you want. So this is going to be more general unitary operator for the single qubit system, and we can readily extend it to any multi-qubit case you want. Okay, so just look at this circuit. Here u of pi by 2, 0, pi, 0. So what is the meaning? First, pi by 2 tells you it is theta value. Okay, it is theta. So we have to use this numpy package, np.py. And then what we are doing, like theta is pi by 2, phi is 0, lambda is pi. And what is this 0? This 0 tells you which qubit you are going to operate. Since we are dealing with only one qubit, so we have to use 0 here. And it is going to draw the circuit. And we can use EMPL here. So this is what it is. So you can use this general unitary operator to whatever gate you want to construct, that you can do with this unitary operator, right? And then if you want to look at algorithms, like for example, this Jose algorithm, there also you can construct the quantum circuit for any algorithm. For example, this is a full circuit for Jose algorithm. And if you want to construct a circuit, just you can use this Qiskit visualization package. Then you can construct whatever circuit you want with this. And you measure the final system and you can see what is the output it is going to give you as the histogram or else the block multivector or array to LaTeX command. This is what from my side for Qiskit. I think it might have given you some insight about how to use this Qiskit visualization package and how to represent quantum states as well as the gates, right? Any questions?
Yes, sir. There are 3 questions that is being posted in the chat.
Okay. I will just go to the chat.
Can I read now?
Oh, yeah.
Yeah, one is from Abhirami madam asking like, can we import images as input to Qiskit?
Images. Yes, like this Jupyter notebook, you can import anything, right? This Jupyter notebook. Here, like in this along this line, wherever you want some images or anything, or some writing, anything you can add with this Jupyter notebook. It is more like if you are working with a Python spider, for example. Yeah, spider, if you are working like you are writing a code and just running and seeing this, right? But Jupyter notebook, you can add anything, images. Then next.
Next question is from Amrita madam asking how to encode an image in Qiskit.
Encode an image in Qiskit. Actually, for encoding image is not a big deal for Qiskit. Qiskit is to like simulate quantum system, right? It is to simulate quantum, construct a quantum circuit, and like we are going to see what happens after the after complete circuit and what will be the output of some algorithm. It is used for that one. For just importing images, you can just go through Google. It is not a big deal with Qiskit, right? Qiskit is for constructing a circuit and realize some algorithms. Jupyter notebook, you can all the time you can use it. You don't need Qiskit for that, for importing some images.
Another one general question has been asked from Amrita madam stating like, which is the best source to learn working and installation of Qiskit step by step?
Yeah, you go to this GitHub page, right? Git textbook, and it is directing you to this GitHub page. Here, everything is discussed, installation, everything. And you, if you have any further doubts, you can even mail to me. My mail ID is given, right?
I have shared your mail ID, sir.
Yeah, good. So this GitHub page is discussing everything, this installation part and this textbook. Full like whatever algorithms you want to discuss, everything is there in this. And like if you are reading some algorithms, like let's say from Nielsen Chung book, it may be a little laborious, like it's not for the beginners. But this Qiskit textbook like discusses clean every algorithms. So you can get the full installation things as well as the understanding of every algorithms with this Qiskit textbook. You go to this GitHub page, that's enough. Anything else?
One question from my side, like as you are explaining from IBM, do you have any idea like how fabricate helps in case of this quantum computer?
Quantum computer, like it has many realizations. Like some people will be working with optical qubits. For example, in our lab, we are working with
Okay.
optical qubits, like in the polarization degrees of freedom or orbital angular momentum. So our idea is something different. And some people will be working with the superconducting qubits or trapped ion qubits. It is which realization you are working with. It is up to that, right?
So how complex the circuit will be?
Circuit complexity, like all the things, like when you whatever things you are working, you have to understand one thing, like that you have you heard about this dimensions of criteria?
No.
Anybody knows that? Like first thing is like you are constructing a realizing some qubits. That can be anything, like it may be an optical qubit, trapped ion qubit, or superconducting qubit, or whatever. The thing is like the gate operation time and the decoherence time are very important, right? When you have a qubit, ideally, like when you are working with pen and paper, you are writing its quantum state. But when you are preparing the quantum system experimentally, what happens is the system will start to interact with the environment. When it interact with, like it is like a pendulum, like you take a pendulum, you completely confined it to some closed space, like it will be continuously oscillating, but it is kept in some drift medium. That pendulum will, like that oscillation will be dropping, that amplitude will be dropping down, and finally it will come to the rest, right? Same thing happens to the quantum systems. Like when you have an open quantum system, it start to interact with this environment. Due to this environment, the system will start to decohere, right? You may be creating some quantum state, but afterwards, when due to the interaction, the system will start to decohere, and you will finally end up with some state which is out of this quantum superposition. You can't find superposition in that one. So you have to do all the gate operations before the system is decohering, right? And you will be having series of gate operations in your circuit. So how do you every gate has some finite time to operate on the system. So what we have to do, general requirement is the gate operation time should be very, very less compared to this decoherence time. But even after that, like if you do that, you will be getting some state, but that may be unwanted. So what we have to do something, we have to do something called quantum error correction, and multiple things comes into the picture. Like you have to do this quantum error correction part. After this correcting errors, like for that you have to have some ancilla qubits, right? For every qubit, you will be having some 10 ancilla qubits to correct the errors. So these are the things involved. Like you have to have consider this quantum decoherence time and the gate operation times and how you are correcting errors. These are the things comes into the picture when you are thinking about the actual realization.
And there is one more question from Abhirami ma'am. Is Qiskit is good to work on quantum convolutional neural network?
Sorry, I'm not working on that line. Like Qiskit, we can like it will help you to some level, but I'm not sure about this part.
Okay, so thank you. And is there another one question from Manimali ma'am stating like, sir, what about the job opportunities and role of job and package related to Qiskit?
Qiskit,
Any study materials or resources related to quantum machine learning?
quantum machine learning, we can start with this Qiskit and you can learn. But job opportunities just with Qiskit, I'm not sure like how good it is. Like we are running a MTech program here. You are asking about the job opportunity, right?
Yeah, that's what the question has been posed. Like,
Okay, okay.
sir, what
So
about the
the
job
general
opportunities and role of job?
yeah, we are running MTech program here on quantum technology. Like just with Qiskit, like we are introducing this quantum computing part in 2 semesters. First semester, I'm introducing this quantum, see, I'm getting students from multiple background. Half of them are from physics background, And engineering, we have every possible streams from engineering. So I have to give background of this physics, quantum mechanics, and then I will then take them to the algorithm. Next semester, I'm introducing this kit and giving some short projects with that. But that alone will not help them to get some job, right? Then next semester, in the third and fourth semester, they are going like, we are not sending our students outside for this internship and all. We are giving a proper project for 1 year, and they are working on some experimental areas, right? Some optical qubits. They have to work and they have to demonstrate something. With that expertise, they are getting placed in DRDO organizations like CDAC and other things, as well as some private companies. But whoever is coming for job recruitment to our department, our general rule is like we are setting this upper limit year by year. We started this program 4 years back. That time the average package was around 9 lakhs. But just with the KISS kit, I'm not guarantee you that one, right? And current last year, one guy got till 18 lakhs package. Two students got 18 lakh package, and he had multiple opportunities also. And I can say the average package was around 12 lakhs per annum. But all of them worked with some implementations, some cryptography, quantum cryptography, quantum computing, or else this entangled photon source development, and many things. So I can't guarantee you like just with Qiskit you will get some opportunity. Maybe with machine learning, and if you are including like you have to do something challenging, then only you can go for this. And you should have that kind of collaborations also, I can say.
Thank you, sir. There is another question like from Amrita madam stating, sir, few days back I saw Python run platform on IBM.com,
Okay.
Qiskit platform, but now it is not available there. Now only Composer is available. Am I going somewhere wrong or it's been removed from there?
Or the Qiskit you are saying, right?
Yeah. I saw Python run platform on IBM.com Qiskit
I
platform.
understand our question. Like sometimes back, like year back when I was teaching this Qiskit, I was working with this Qiskit textbook. For example, I'll show it you here, right? Qiskit. And yeah, it is directing you to this website, right? You look at this third one, Qiskit textbook. Actually, this IBM itself, they closed this website. Earlier, this textbook was so clean, like it is like a PDF. When you're reading in PDF, how it looked like that kind of thing it was there. And it was interactive also. You can even work there also. But now, the IBM closed this website completely, and they have given this GitHub. You have to get everything from this GitHub page. Anything else?
That's also, that's all the questions that is being posed.
Okay. Okay, so then still if there are any questions, like you can drop a mail to me.
Sure, sir, sure. So before winding the session, I would like to invite our coordinator, Dr. K. Rama, Dean Research, for giving few instructions to all the participants. Rama, sir.
Okay. Thank you very much, madam. On behalf of our management and the participant and on behalf of our team members, I thank Dr. Srinivas sir for a wonderful presentation of the topic given to him. Thank you, sir. Thank you very much, sir.
Thank you for the opportunity, sir. Thank you, Shilpa, and
My
thank you.
dear participants, I hope the co-coordinator Sumatra Murugan might have given some instruction to be followed. Number one, there is a small change in timing for tomorrow's session based on the request from Dr. Sarmu Sundaram of Australia, and also subsequently we asked the AICTE for their approval. Based on that, we changed the timing. First session will start from 2 to 3:30 p.m. and second session will on from 6 to 7:30 p.m. There's a change. I sent a mail to all the participants today morning. Number two, we have posted the attendance for first day, 2nd of December. We post the attendance. And that in the attendance, there is a small mixing with initial and everything. So I request the participant, whatever the name you are given in the portal, in the same name only you are given, you have to give the attendance. I hope participant will understand our difficulties. It is very difficult to match these names. Sometimes very few faculty members, around 8 faculty members, we found some difficult to understand who is this attendance. So with these few words, once again I thank Dr. Srinivasa sir, and I thank all the participants for listening to Dr. Srinivasa lectures, and thank Dr. Sumatra madam, spoke coordinator, and my team members for this excellent arrangement. Thank you one and all. Thank you.
As a concluding remark, I'm so thankful to Srinivasan sir, because I personally know at what tough phase he's having to come to the department today and be with us for these 3 hours, taking both the sessions. And thank you for your excellent and insightful sessions, sir. So you have took the session starting from the polarization states of light till that. And one thing I just wanted to mention, that the Alice to Bob we heard only in terms of cryptography, and I was impressed how you have discussed the quantum theory in terms of this Alice and Bob. And thank you for giving the hands-on demonstration on the programming tool QUBITS. Hope it might have provoked a few participants at least to work on it and to study the materials that whatever you have shown to us. Thank you so much, Srinivasan sir.
Thank you so much for the opportunities, ma'am.
Yes, and on behalf of participants, I once again thank you and hope to have you in future events as well. Thank you, sir. And thank you, participants, and hope so that